Okay, linear momentum. Don't ask me why the letter P we use for linear momentum. You figure L will make sense, but L we use it for something else. Definition of linear momentum. Momentum is a vector, is equal to mass times velocity. Linear momentum is really how much moving power an object has. That's what linear momentum. And it depends on two things, on the mass of the object and how fast the object is moving. Here's a story, true story here. There was an incident about 5-6 years or more than that, probably 10 years ago. East Long Meadow, that intersection. You know that six-way horrible intersection? There was a softball game was going on, or a baseball game was going on. A guy was driving one of those garbage trucks, you know. It's a heavy truck, and he's going like 20 miles per hour. There were two sisters in front of him. He was watching the game, wasn't looking. He hit their car, crushed their car, ended up killing both of them. And you look at the damage of the car they were sitting in. I mean, the damage looks like unbelievable. And people going, how fast was he going? It really doesn't have to, he doesn't have to be going that fast to cause that much damage. So I'll show you with a car going at 30 miles per hour, how much power does it have? How much damage can it do? So if a car has a mass, let's say 1,200 kilogram, this is a small car, going at 20 miles per hour. Let's see how much moving power does it have. What is the linear momentum? The linear momentum of that car is the mass of the car, which is 1,200. And now I need to convert that velocity from miles per hour to meters per second. We divide by what? 2.24. So 20 divided by 2.24. And that's 8.9 meters per second. So times 8.9 meters per second. And the result is 10714, so roughly 10,700. The unit for that, what's the unit for mass? Kilogram. And what's the unit for velocity? Meters per second. So kilogram times meters per second. That's the unit for linear momentum. That's how much power that car has with it, moving power. Now replace that with the garbage truck I was talking about. If it's loaded here, there's a truck. And if it's loaded, it probably weighs about, I don't know, let's say it's 1,500 kilogram, 15,000 kilogram. They've been collecting garbage all day long. And let's say it's moving at speed of 20 miles per hour too. And again, the 20 miles per hour is 8.9. So how much linear momentum that truck will have? It's going to be 15,000 times 8.9. It's so this number we say approximately 10,700 if we carry 3 decimal place or 3 significant digit. 3 significant digit, this will be what? 134,000. 134,000 kilogram meter per second. Now let me rephrase the question, because people couldn't believe the damage actually their car had. So how fast the top car must move to produce the same linear momentum as the truck. We're talking about the car on the top there. How fast does that car have to move to generate that much linear momentum? Because that will give you an idea why the damage is so bad there when you see the speed.
Is the speed 8.4 or 8.9?
8.9. Yep. It's 20. I convert that by dividing by 2.24. I think 8.93. I think. So let's see. We want the 1,200 kilogram car to move at what speed times v to generate a linear momentum of 134,000. So the velocity of the car will have to be what? 134,000 divided by 1,200. The car has to be going at a speed of roughly, ready for this number? 1,112 meters per second. Multiply that by 2.24. It has to be going approximately 225 miles per hour. Imagine if you stopped at the light and a car came from behind at 225 miles per hour, or 250, I'm sorry, not 225, 250. A car came in at 250 miles per hour, hit you from behind. Imagine the damage. That's what that truck has for moving power. So it doesn't have to be going that fast to cause that much damage. But when people saw the damage, like, oh my goodness, look at the car, he must have been flying. No, you look at the weight of that. You got a different number?
Yeah, I'm getting different answers.
What did you get?
Well, I also don't understand why we divided it by 2.24 or whatever.
That's 20 miles per hour to convert to meters per second.
Oh, okay. I didn't
Yep.
realize where that came from.
20 divided by 2.24 to change it to meters per second, 8.93 roughly. You know,
So we did the 134,000 divided by
1,200.
1,200?
Yeah, because that's the mass of the car, right?
Yeah.
What is that number different? 134,000. Let me just
Yeah,
double.
and then when I divide that by 2.24.
Multiply now.
Oh, why did I
Yep.
divide it?
Because you get meters
Okay,
per
yeah.
second to miles per hours, right? This from miles per hours to meters you divide. From meters to miles you multiply.
Oh, okay, I was just doing it off.
Yep. So the car actually, this truck causes much damage as a car, like a normal car, going 250 miles per hour. Yep. I'm telling you, that was a big event. That when that happened, that incident there, that was a big thing. Everyone wanted to hang that person like, he must have been speeding to cause that much damage. He must have been going 80 miles an hour. No, people, it doesn't have to be going that much faster. Depends how heavy that load is. So when you see these 18-wheelers coming your way at 50 miles per hour, you can't really play games with them. Or a train, sometimes you watch a train hitting, a car will get stuck on the track, the train will hit it, that car is gone, like nothing, a matchbox. Because that train is going at good speed. Go back to 9/11. These planes that hit the towers, look how fast they're going, 450 miles per hour, and look at the mass of that plane. The power of that is bigger than any bomb we probably have in the U.S., with the exception of nuclear weapons. That's how much damage in them.
So that truck is going 20 miles per hour.
The same as the
That
car.
much. So then the top car would have to be going 250 miles per
To
hour.
create the same damage.
To do the same amount.
Yep.
That's crazy.
Yeah, because why? Because the truck knows 15,000 kilogram I made it, which is about 10 times, or 10 of these, more than 10 of these cars, 12 of these cars, much, much heavier. Of course, if it's much heavier, it's like taking that number now, multiply it by 12 that speed. You know. This actually aggravates me with sports, because you see that sometimes. I know I follow football, I'm sure some of you do that, roughing the kicker or roughing the passer. Well, when somebody who's about 280 pounds jumps in the air and want to tackle Tom Brady, he can't just stop. If you just put your knees to stop, you just shatter your knees, because you get that much moving power. They're not small, they're big people, and they go in a good speed. They're going 10 meters per second, 10, 12 miles per hour, running at good speed. And they're, 300 pounds, 350 pounds. They can't just stop because of that equation. Momentum. Your momentum is going to carry you. And sometimes they do intentionally, but 9 out of 10 times they really can't help it. You cannot stop. You can't change directions. Again, why P, I'm not sure. Maybe because power, moving power, I don't know. But we use the letter P for linear momentum. We'll use L down the road in case you want. Why didn't we use L here? You'll see that coming up next. We'll use it for something else. Okay, let's try maybe another example here. Here's the example. It says, at a city park, a person throws some bread into a duck pond. Ooh. 2 4-kilogram ducks and 9-kilogram goose. Paddle rapidly toward the bread that you throw. So we have 2 ducks and 1 goose. Here we go. This is a duck. I just put D for duck. I can't really draw. There is another duck. D, they're swimming. And a little chubby goose there. G for goose. The bread is right here. So this one's going this way, this one's going this way, this one's going that way. Remember, maybe I didn't mention that, I just put it there. Linear momentum is actually a vector, which means what? The direction of that vector is going to be the same direction as the velocity. So if the car is going to the right, the linear momentum will be going to the right. It's the same direction. So these 3 animals here, the 2 ducks and 1 goose there, paddling toward the bread there. Now, if the duck swims, this is the velocity of each duck, of a speed of 1.10 meters per second. This duck also has the same speed, 1.10 meters per second. And the goose can swim at 1.3 meters per second, faster. Find the magnitude and direction of the total momentum of the 3 birds. What is the magnitude and direction of the net momentum, the total momentum? Let's label these as duck. The first one is number 1, this is number 2, and the goose is number 3. Now, let's see what will happen. What is the net result? This is what we did a while ago in the lab or in the homework, vector addition. Duck number 1, it's moving to the down, right? So it's going to have a linear momentum which way? Down. We'll calculate what that is. That's number 1 here. Duck number 2 is going which way? To the right. It's going to have a linear momentum to the right. And the goose, that's number 2 here, is going upward north, is going to have a linear momentum going in that direction. And once we know what the 3 values are, we can do vector addition to see what the net result is. Remember, linear momentum is a vector. So duck 1, we'll call D1. Duck 1 has a linear momentum, mass times the velocity. Do we know what the mass of each duck? Somewhere the mass is given. I just got to hunt it down.
The book says 4 kilograms.
And the goose is what, 9? The duck is, the mass of the duck is 4 kilogram. And the mass of the goose is 9 kilogram. So let's look at duck number 1. It's going to have a linear momentum. Again, it's coming down. Let's call it P1, linear momentum for duck 1. P1 for duck 1. You know 1 is a duck. So the linear momentum for duck number 1 It's the mass of the duck, which is 4, times the velocity, which is 1.10, and that's what, 4.4? And it's pointing down. So this will have a value of 4.40 down. Duck number 2, it has linear momentum, mass times velocity. It's the same thing. 4 times 1.10, that's 4.40. Which way? To the right. And linear momentum for goose number 1, which is the third animal. It's the mass of it times the velocity. The mass is 9, the velocity is 1.3. Is it 11.7? Up. So now if I find the result, to find the result, what do we have? We have basically two vectors, the net result, and we'll find the equivalent of them. We got 4.4 to the right. There's nothing that's going to cancel that. There's nothing to the left to cancel that. But we have 11.7 up and 4.4 down. 11.7 minus the 4.4, because in opposite direction. The net result is what? Is it 7.3 up? So notice our resulting vector is going to be which quadrant? X is positive, Y is positive. Which quadrant is that? Quadrant 1. So the resulting vector is going to be in that direction. That's the value of it. This is P, the net result, and this is the angle theta. They're asking for both. What is the value of that net vector, the linear momentum, and what's the direction of it? So to find P, maybe I'll use this one. Since you know the x and the y, this is 7.30. This is 4.4. It is the square root of 7.30 squared plus 4.4 squared. The result is, we take the square root of that, 8.52, right? Again, kilogram, meters per second, not Newton, meters per second. Kilogram, meters per second. Units for it, mass is kilogram, velocity is meters per second. Theta, you're in the first quadrant, there's no adjustment needed. The inverse tangent of the y value over the x value. Roughly 58.9 degrees. That's what the net result is. So if that bread somehow, when they go to hit it, if each one like touch it with their beak and they hit it, that bread should go in that direction. All three of them, if they bump there, it should go in that direction. I'm going to combine color sections together because I'm not just going to make a video for linear momentum. So maybe I'll add to it momentum and Newton's second law. So that'll be sections 9.1 and 9.2, you know. I want to keep individual videos for each one. Momentum and Newton's second law. If you remember, Newton's second law says the net force equals mass times acceleration. Okay. How do you find acceleration? What's acceleration? Isn't acceleration change in velocity over change in time? So I can say change in velocity divided by time. What does change in velocity means to you? Isn't that v final minus v initial divided by time? And if you multiply it by m, that'll be m times v final minus m times v initial divided by t.
Why don't you apply the m to the t as well?
Can't. This is m over 1. When you multiply a fraction, the top times the top, the bottom times the bottom. Now, we just said linear momentum P equals what? Mass times velocity. So this is mass times velocity. See it? And that's mass times velocity. But this is the final velocity. So if I do that substitution, that's really my final linear momentum. And this is what? My initial linear momentum. And what is final minus initial? Isn't that the change in linear momentum? So that's the equation I was trying to derive. Is the change in linear momentum divided by time. Now, where do we use that? Take baseball. Let's look at the Red Sox. They stink, I know. I'm on video saying that. Well, this year they do stink, and I'm a big fan of them. But they're pathetic. So, let's watch and see what happens. A pitcher will throw the ball. Buckholz will throw the ball at a batter there. This is the bat here. So the ball is coming at the bat at a speed, velocity, I don't know, of 90 miles per hour. The bat hits the ball, and the ball now goes backward now in this direction at a speed, velocity of, let's assume the velocity is, I don't know, 105 miles per hour. Usually the contact time between the baseball and the bat is really short. It's less than like 1/100th of a second. So let's say the contact time, t, where the ball was making contact with that bat, is 0.005 second. Very quick time.
I have a question.
Yes.
Before you move forward, is the 90 miles per hour the initial velocity, or is it the velocity when the bat hit?
Well, that's when the ball hits the bat,
Contact
yep,
with the bat.
when it hits the bat. It's
And
coming
then
in
when
right
the
before it
bat
hits,
hits the ball, it's
and it leaves in that direction, 105.
Okay. So if I draw an arrow like to the right with
So,
90, that's
That's like, you're looking at it like this, the bat. You draw an arrow, the ball coming in this way
Okay.
of 90 miles per hour. And you draw one that way of 105 miles per hour. Yep. Now, that force between the bat, by the way, if you watch this in slow motion, this is what happens. I'll just try to show you. The ball comes in, there's no force. It's not making contact with the bat. Nothing, 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 nothing. Then it touches the bat. Once it touches the bat, that ball starts to push on the bat bends a little bit, like in golf, the same thing. Then it will stop, then it will go forward, and it will go backward in that direction. So if you watch really that force between the ball and the bat, if you're monitoring that, it will look like this. 0, 0, 0 till it touches the bat. Once it touches the bat, start to rise, to increase to a certain value, then start to decrease, then it's back to 0 once the ball leaves the bat. That's if you watch on slow motion. If you actually watch the ball, you'll see the ball kind of self-wrapped itself around the bat, like it bends a little bit. It's like a rubber there. It bends around the bat, then it goes forward. We might have a picture of that here. Yep. Can you see that picture? You know, kind of bends around that one, you know. But when you hit that impact, that time is really short, usually about like 1 second, 1 millisecond, like 100,000th of a second, millisecond. So what is the average force? Now, what we're looking for, the average force. When I say the average force, I'm looking for a height here. What number, constant force, that if I take the width times the height here, if I multiply this height by the width, will give me the same area as this if I calculate the correct value. That's what I'm looking for. What is that height? What's this force? What's the height of it? Average force. That will give me the same. I'm looking to say, okay, this is with the start of the impact, this is the end of it. So if I multiply the width times the height, I'll get an area. I want to find out what that height, that'll give me the same effect as calculating that area, the same result. Well, we go to Newton's second law, which says the net force equals the change in linear momentum over time, which is mass times V final minus mass times V initial divided by T. So let's look at the mass here. The baseball usually has a mass, forgot exactly the mass of a baseball, but it's about let's see if we can Google that, look for it. Baseball mass, 145 grams. The mass of a baseball is roughly 145 grams. So let's see what the momentum is. The final velocity. Well, notice it's going to the left. The force is going to indicate which direction. When you're hitting the ball, you're pushing it to the left. So my force should be going to the left. That's where the bat's, I'm swinging the bat. That's why the ball is going to the left. So my value is going to be negative to indicate which way. It's going to the left. So it's going to be the mass, which is 0.145. times the final velocity. The final velocity is 105. I got to change that to meters per second. That's miles per hour. You divide it by 2.24. It's 46.9. There will be a negative 46.9. Why negative? Which way is it going? To the left, right? Minus the mass, which is 0.145. times the velocity, initial velocity, which is to the right, that's positive, right? What is 90 divided by 2.24? 40.2. All of that divided by the time it took, which is 0.005 second. So the average force of impact during that time is going to be I came up with 2526 Newton, if I did the math correctly. Negative. And negative to indicate you were going to the left. So during that time, the bat has an impact, which is, we know that's not the case. It starts slow, then it goes to a maximum value. So it does get higher than that value, does get lower than that, but as an average value during that time, has an average value of 2,526 Newton during that impact. Now let me look at that equation here again one more time. The average force, we said, equals to a change in linear momentum divided by t. Now I don't like fractions. To get rid of that t in the bottom, what can I do? Multiply by what? T. So the average force times the time equals the change of linear momentum. Or the average force times the time equals the change in momentum. That's mv final minus mv initial. In physics, this has a name. This one we call that impulse. So if you're doing the homework and you hear the word impulse, we use I for impulse. It is equal to the average force times the time, which happens to equal to this one too, mass times violent velocity, or change in potential energy. But we call that the impulse. So you might see a homework assignment says, find the impulse. So you can either use this, or you can use that one, either one. Let's try a couple more examples, then we'll stop here and go to the lab. I'm doing like about 3 sections here together. Let's take another example and see what we have. Oh, told you my book is coming apart now. It's all right. Jumping for joy. How's that? Woohoo! Today, 60% of the course is done. You're jumping for joy. Let's see what happened. After winning a prize on a game show, we have a contestant here, 72 kilogram. Gets really excited. Jumps for joy. Jumps up in the air. Woohoo! I won. It says if the jump results in, this is part A, if the jump, so he jumps upward, up there, if the jump results in an upward speed of 2.1 meters per second. What is the impulse? Notice the impulse. That's the first question. Part B here, before the jump, the floor actually was pushing upward. The floor exerts an upward force that's why just standing there. Of what? How big the force do you think when you're standing on it?
10 units,
No, think again.
3 newtons.
Not a number. You're standing on the floor.
It's the normal force.
Oh, the normal force. So if you're standing on the floor, what do you have? You have what pushing down? Your weight down, which is mg. That means the floor is pushing up on you with the value of mg. Jimbo.
AC.
Yep. So if the floor pushes up,
If it doesn't, I'm gonna fall off.
of mg
Crazy.
on the contestant, here we go. What additional, here we go. Mr. McDonald was my teacher in 1978. What additional average force does the floor exert on the contestant? Because to jump, you got to bend down, push hard. Does the floor on the contestant if he pushes down, the contestant here, pushing down on the floor for 0.3 seconds before he jumps. Tired of writing too much stuff there. Let's begin with the first one. The first one is the easier of the two questions to look at first. If he jumps, he goes, hey, you're the winner. The jump results in upward speed of 2.1 meters per second. What is the impulse? Well, initially, when the contestant was on the ground, what was his initial speed? 0. So impulse, you can calculate impulse two ways. You can take the average force times the time. In part A, we have no idea what the time or the average force. You go, well, you know the time here. That's part B. I didn't get to it. Has nothing to do with A. Or you can say it's the change of linear momentum. You can use either one. I might want to use this one, the change of linear momentum, which is what? The mass times V final minus the mass times V initial. Well, the mass of the person is what? 72. What was his final velocity when he jumped? In part A, it says he jumped with a speed of what? 2.1 minus the mass, which is 72. What was the initial velocity? 0. That tells me what my impulse is. 72 times 2.1, which is approximately, rounding to the significant digit, 150 kilogram meters per second. And if you want to indicate which direction, it's which way? Upward, so in the y direction. I can write up or the y direction, you know. So that's part A. Well, how do we calculate what the average force is? Well, let's look at that equation. So this is A. This equation says what? Impulse equals the average force times time. Do we know what the impulse is? Which is what? 150. Do we know what the average force is? We're looking for it. Do we know what the time is? Which is what? 0.36. Can we get what the average force? Do the math for that one. And what are you going to have?
Should we use the 150 or?
Well, you can use the real numbers. But it ended up being roughly what? 420 Newton. And what is that force? Which direction, by the way? What do you think the force pointing? Better be upward. Better be pushing upward in the right direction. So that person has to generate an additional force of 420 Newton to get him to go upward. I say, ooh, I won. You know? And we'll stop with this one here so we can go to the lab. We did like 3 sections, 3 short sections. I combined them together. So this will be one video.